Good morning everyone. This is Ravan Kumar and my topics for the video presentation are first order stationary process, second order and wide sense stationarity, nth order and sixth sense stationarity. Now we go through the introduction of the random process. Introduction to random process. A random process is a collection of random variables indexed by time or space. Now, examples are thermal noise in resistors, speech and communication signals. Random process often studied for their statistical properties. And what is stationary process? A process is called stationary if its statistical properties do not change with time. This means uh, the, the properties that do not change with time, then it's called stationary. This means the mean and variance are constant. Autocorrelation depends only on time difference. Stationarity it simplifies analysis, modeling of random signals. And now go through the first order stationary process definition. If a process is first order stationary if its mean value is constant over time, and if the mean value is constant over the time, then it is called first order stationary. Mathematically we show that expectation of x of t is equal to constant. Expectation of x of t is equal to constant. Example, white noise or any zero mean random signal. Graphically, the signal fluctuates but has a steady average level. Example for first order stationary. If the mean mu x of t is equal to 0 for all t, the process is first order stationary. For example, x of t is equal to a cos of omega t plus theta, comma, where theta is uniformly distributed over 0, 2 pi. That is mean is equal to 0. Hence first order stationary. And in first order stationary. Now we can go through the second order wide sense stationary. Second order definition. A process is wide sense stationary if the following conditions are satisfied. If the first mean is constant and the autocorrelation depends only on time difference tau, and rxx of t1 comma t2 is equal to rxx of t1 minus t2. This simplifies analysis in frequency domain, that is power spectral density. This is what this equation shows. Rxx of t1 comma t2 is equal to rxx of t1 minus t2 in wide sense stationary, second order and wide sense stationary. Now go through the autocorrelation function. You know that autocorrelation measures similarity between signal values at different times. We know that autocorrelation measures similarity between signals where values at different times. That equation shows rxx of tau is equal to expectation of x of t into x of t plus tau. For wide sense stationary, rxx of tau depends only on tau. Depends only on tau. Depends only on tau, not on absolute time. Go through the nth order stationarity definition. A process is nth order stationary if its joint probability distribution of n samples is invariant under time shift. For example, p of x of t1 comma x of t2 comma and so on x of tn is equal to p of x of t1 plus tau comma x of t2 plus tau and so on x of tn plus tau. That is, probability distribution of n samples is invariant under time shift. Importance of nth order stationarity. It helps in the modeling higher order dependencies and used in non-linear signal analysis. That it is used in the non-linear signal analysis. And strict sense stationarity implies all orders are stationary. Going through the strict sense stationary definition. A process is strictly stationary if its statistical properties are invariant to any time shift. That is, all movements and distributions remains the same for any shift tau. This is a stronger condition than wide sense stationary. We see the conditions. First order comparison summary. First order stationary has a constant mean. We see that first order it has condition constant mean, and the second order, that is wide sense stationary, constant mean plus autocorrelation depends only on tau. Now nth order conditions are all n dimensional distributions invariant. What? All n dimensional distributions are invariant. Now strict sense stationary conditions. All statistical properties are invariant. All statistical properties are invariant. Now we can go through the real life examples. What? White Gaussian noise, that is strictly stationary. It comes under the strictly stationary. And speech signals approx wide sense stationary in short intervals. Communication channels often modeled as wide sense stationary. Random errors in measurements usually stationary. You see that random errors in measurements that usually in stationary. Summary. A stationary process simply analysis in communications and signal processing. That is, first order comes to mean constant, second order the mean and autocorrelation stable, strict sense conditions, complete invariance. Assume wide sense stationary assumption is practical for most real world systems. And differences you can go through, and thank you.